Hello everyone, this is Mike Dowding with the SD Minds Physics Department, and we're continuing our discussions with Chapter 8 Material. And today's discussion will cover thermal energy. And what we're going to do is, first of all, go back and look at the previous conservation of energy equation that we've been using, which says the energy that we start with has to equal the energy that we end with in the system. And that statement is not going to change. However, we are going to have to change the way that we keep track of the energy. And it's at this point that the book takes the combination of the two energies, kinetic and potential, and puts it together into a single term that we're going to call mechanical energy. Now, this is not going to change anything that we've had in any of the previous equations or discussions, but it's worth mentioning that this combination of kinetic and potential energy, these are the good kinds of energies that we can make use of. In other words, if we want to physically pick something up and move it, in other words, if we're, say, out on a construction site and we want to pick up a large rock or something like that, pick it up, move it, to do that, picking it up would mean changing the potential energy of that object, and to move it would mean changing the kinetic energy of the object. And we've seen in previous examples that we can basically trade off back and forth between the two types of energy by doing work. However, this expression is only valid if we're working in a system that does not have any non-conservative forces. So I guess another way to say that is this expression would only work if we were in a system that involved conservative forces. And our non-conservative forces, those were the forces that do not conserve the amount of work that's done over a closed path. And in a previous video, we saw that friction was one of those forces. Friction will never give energy to the system, it will always take away. And some other types of non-conservative forces that are out there, we have air resistance. I didn't spell that correctly. So we have air resistance, which is not something that's really been considered much in this course, mainly because the mathematics behind the dynamics of air resistance are not that easy, except that when it comes to energy, air resistance acts in a resistive manner, and it's going to generate heat, very similar to how friction will generate heat. And then if you work with other fluids like water, there is a similar term that we call drag that describes how that fluid will resist the motion of the object that is running through it. But all three of these will produce heat as a result. And heat is the transfer of thermal energy from one object to another, or from one medium to another. And that thermal energy, well, conservation of energy says we can't create or destroy, the energy already has to be present. And the energy that we start with in our system, well, that's going to be a combination of the initial kinetic and the initial potential. If we're going to generate thermal energy, then that generation of thermal energy, we're going to have to treat that like a byproduct and add it to the other side. And the main consequence of this is that the initial mechanical energy of our system is going to be larger than the final mechanical energy of the system. I guess we could call that ME for mechanical energy. But that combination of the initial has to be greater than the final mechanical energy if we are to have thermal energy as a byproduct of the system. And unfortunately, this is very much a real-world concern, because when we do go out to do work in a constructive sense, picking things up, moving things around, we start off with a finite amount of mechanical energy in our system, and the more and more that we do work, the more and more thermal energy that we produce, until eventually we completely run out of mechanical energy in the system, and then we have to go out and buy more. Quite literally, we have to go and collect more energy so that we can start the process over again. And that energy collection comes in many different forms: fossil fuels, wind, solar, geothermal. All of those are viable means of collecting the energy. But ultimately, with any kind of mechanical system and moving parts, we're going to have continuous energy loss due to things like friction and air resistance. And that's not to say that we're losing energy in the system. The energy is going right back into the system as thermal energy. The problem with thermal energy is that it's not as efficient to collect it and use it as some of the other forms of energy that we collect, like fossil fuels. So now we have an updated expression for the conservation of energy that we're going to see in these problems. And what I want to know is if these amounts of thermal energy are being produced by these resistive forces, then is there a way to take something like a friction force and figure out how much heat it will generate? And the important part to this equation is we have the change in thermal energy written as a delta expression. So keep that in mind. This is a change in thermal energy. And anytime we have a change in any kind of energy, that means that work has been done. And we know from our discussions with these last two chapters how we can evaluate work. So what we're going to do is we're going to go back to our chapter 7 method of evaluating work and see if we can't apply that to our friction force and find out how much thermal energy has been generated. To do that, we'll set up an example problem. Here we have a mass of m. If we need a value, we'll go ahead and put that in there. And we will have this mass start moving to the right with an initial velocity of 5 meters per second, but it's moving over a rough surface, and that rough surface has a kinetic coefficient of 0.3. So as our block slides across the surface, friction is going to oppose the direction of motion, and we will be using kinetic friction because we are moving. But because friction is opposing the motion, friction is going to cause us to slow down until eventually our mass gets to some final location, which we'll call D, and the final velocity has gone to 0. Now the reason I choose to do this on a flat horizontal surface is not just to make the math easier, but it's to show that the combination of initial and final mechanical energies are going to have the same potential values. Because we're on a flat surface, we are not changing our vertical positioning, and so really if I wanted to, I could just say that the mass is currently at a height of 0, and so both the initial and the final potential energies are 0. But even if they weren't, we maintain the same height the entire way through, and so the change in potential energy would be 0 for the system. And that means there are only 2 energies that we have to consider. What kinetic energy did we start with versus what kinetic energy did we end with? And what I'm doing here is I'm using our conservation of energy equation. This is before the update using thermal energy. And we've just got done arguing that our potential energy values should both be 0. So if our conservation of energy expression is to be satisfied, this says that our initial and our final kinetic energy should be equal to each other. Problem there is that our final kinetic energy is 0 because we eventually come to a stop. And I have values for M and V initial that tell me that the initial kinetic energy is not 0. Yet I have an expression that's set equal to 0, so something must be wrong. And the thing that's wrong is this. Because we have friction in the system, we now have to consider the fact that some amount of thermal energy has been generated. And now we can see how much thermal energy has been generated, because our equation, as it is, says that all the kinetic energy that we started with was lost due to friction. And friction is going to take away that kinetic energy, but it can't hold on to it. It has to give that energy back to the system right away, and so it's going to do that in the form of heat. We're going to put that energy back into the system as thermal energy. Well, this makes for a pretty easy problem now. I have a mass of 10. I had an initial velocity of 5. And so let's see, 25 and 10 divided by 2, that makes for 125 joules. So we started with 125 joules of kinetic energy, and it was all converted into thermal energy. But that doesn't answer the question that I had before. Is there some way of figuring out how much work friction does in the process? So let's see. We know what our kinetic coefficient is. It's 0.3. And we need to figure out how much work will friction do as we travel that displacement of little d. And back in chapter 7, if we were to apply this to our work expression, remember we had multiple ways of evaluating work done, but the easiest way was to use the magnitude and angle approach. Our friction force, for right now, we'll assume that we know what the magnitude is. Likewise, we'll assume we know what the displacement is. But the important part is the angle relationship. The displacement and the friction force are pointing in opposite directions. That's a cosine 180. Cosine 180 is a -1. And so there is the expression that tells us how much work our friction force is going to do. If we want to take that a step further, we can grab the expression that defines kinetic friction, which is coefficient times normal force. Well, that means I need to know what the normal force is. We know that the normal force has to point normal to the surface, but while we're at it, we may as well start drawing in the other forces in the system as well. Now, granted, this block is moving to the right somehow, so maybe there was some kind of driving force in there, but I'm just worried about what the normal force is. And from a quick sum of forces in the y direction, so this would be chapter 5 material, taking a sum of forces, we see that the normal force is equal to the weight. So that's going to come down into this expression. So we have mu k mg. And so now the work done is negative force of friction times displacement. And that has to be the amount of work that friction does. Okay, well, let's remind ourselves of the definition of work. Work is responsible for the change in kinetic energy. More specifically, net work. Well, so what's the net work? It's the work done by all of the forces in the system. We know how much work friction does. That's the expression that we just found. And how much work are the other forces in the system going to do? How much work is the normal force going to do? Well, the normal force is at a 90-degree angle with respect to displacement. So the moment I put that into our evaluation, cosine of 90 degrees is 0. The normal force doesn't contribute to any work. Likewise, gravity is at a 90-degree angle with respect to the displacement, and so gravity is not going to do any work in this case. There we go. There's the net work. It's just the friction in this case. The work done by friction is responsible for the change in the kinetic energy. Our final kinetic energy was 0. Our initial kinetic energy was based on the initial velocity of our mass. And what we have now is an expression that says we don't need to know the mass. The minus signs are going to drop out, and what we're left with is mu k g d equals half of v naught squared. So what can we do with this? We know what the initial velocity of this block was. We know what the kinetic coefficient was, and so the only thing that we don't know in this expression down here is what was the stopping distance. So that is something that we can solve for. All we have to do is divide each side by mu kg, and we have, let's see, what do we have for our stopping distance? Calculator time. We have 25 divided by 2 divided by 9.8 divided by 0.3 equals 4.25 meters. So given the initial velocity and the coefficient of friction, we can actually work out and predict what the stopping distance of that object is. Another thing that we could do is, back to this same equation, maybe we don't know what the coefficient of the system is. Maybe we don't know what that kinetic coefficient is, but we know that it took 10 meters for this block to come to a halt. So let's say we pick up our mass and we move it to a different surface, and we give the mass the same initial velocity of 5 meters per second, but now it is able to travel a greater distance on this new surface. So this new surface must be smoother if it's able to travel a larger distance. But that means that we now have a way of experimentally measuring what the coefficient of kinetic friction is going to be. These values that we have over here, these are pretty straightforward. These are things that we can control in a laboratory setting. We can't control gravity, obviously, but we know what its value is. So we can start our mass off with 5 meters per second, and whatever this new surface is, we can measure the displacement until it comes to a stop. In this case, we said it was 10 meters. And we end up with a new kinetic coefficient, which is less than half of what the previous one was. Okay, well, that's work though. That's the work done by friction. And we've already done that. We already know what the work done by friction is. We want to know if there's a way to figure out the amount of thermal energy that the friction is going to produce. And, well, we've actually already done it. The change in the energy for the system, we can relate that to the work that's done by friction. Except that friction is always going to do negative work, hence the negative sign up here. The thermal energy that is produced, if we go back up to our expression, the thermal energy that we produce is going to be positive. Remember, friction is going to take some of that initial mechanical energy and convert it into thermal energy. Well, if we take something away, usually if somebody takes something from you, you look on that as kind of a negative thing. So friction takes energy away, but then friction has to give the energy back in the form of thermal energy. And when somebody gives you something, well, that's kind of a positive thing. And this is exactly what happens in the algebra. If you're going to move something from one side to the other, you have to change the sign. And what I've found in my years of teaching, the best way to express this to students is that the change in thermal energy will equal the absolute value of the work that's done by your friction force. And so all that means is that we drop the minus sign from the above situation, and now I have an expression that tells me how much thermal energy has been produced. And we can put all this information back in. We'll have to be careful as to which situation we're working with, but let's go with the 10 meters and the new 0.13 for our coefficient. So 0.13 for the coefficient. We had a mass that was, I can't remember, this is why I write this down, 10 kilograms. Mass of 10 kilograms, 9.8 for gravity, and a displacement of 10. So what does all of that equal? We have 10 times 10 times gravity times 0.13 equals 127.5 joules. And that should not be surprising because if we remember, we started with how much kinetic energy in our system. If I can find it, there it is. We started with 125 joules of kinetic energy in the system, and the thermal energy has to take it all away. Now, matching that up against the answer that I just got down here, I ended up with an extra 2.5 joules somewhere, but my guess is that's probably a rounding error with my algebra. Looking back at my calculator, the coefficient was actually 1.274, and I rounded that up. So let me real quick see what happens if I take that, the 0.1274, and there we go. If I replace this with the 0.1274, then I get 124.97 joules, which arguably is 125. So there we have it. There are two ways that we can figure out the amount of thermal energy that is generated in the system. One way is to look at how much work our resistive force has done. And the only resistive force that we actually have math to back up is friction. We don't really have any equations that we've gone through and derived for air resistance. But that's okay, because another way that we can find the change in thermal energy is to go back and look at how the mechanical energy in the system changes. Because if we do not have the same mechanical energy before and after a given event, then that means that there has to have been some thermal generation in the process. And so we can take the difference in those mechanical energies to tell us what thermal energy in the system is. All right, I'm going to end the video there. We'll have, I think, one more video for the Chapter 8 material. I'm going to do some examples with friction. We'll do some more complex examples, maybe put our mass on an incline, maybe incorporate some springs into some of these problems. Really just put every possible piece of information that we've learned up until now into a single physics problem and see how that treats us. So, see you then.